Good evening, everyone. Before we officially start, could I ask you a favour, which is if you wouldn't mind just moving up a bit. I know the temptation is to be at the back, but if you could, that would be super, just to fill the front. And hopefully we'll get some latecomers as well. Lord Mayor of Dublin City, Councillor Caroline Conroy, Professor Rahmstorf, and everyone here this evening in the round room in the Mansion House, you're all very, very welcome to this EPA Climate Lecture. My name is Ella McSweeney, and I'm delighted to be here with you this evening to hear from Stefan Rahmstorf, Professor of Physics of the Oceans at Potsdam University in Germany, and Head of Earth Systems Analysis at the Potsdam Institute. I'd like to also welcome all of you who are joining us online. We have hundreds of people watching online from all around the world. Pakistan, Latvia, Somalia, Canada, but also, I hope, parts of rural Ireland as well. Thank you very much for joining, and I'm particularly delighted to know that there are a lot of young people watching logged on as well. It is, after all, their future that's at stake. In 1975, the late geochemist Wally Smith Brooker correctly predicted that rising atmospheric carbon dioxide levels would lead to a warming planet. We're playing with an angry beast, he wrote, a climate system that has been shown to be very sensitive. That was way back then. We have all the data we need now. And our speaker today, Stefan Rahmstorf, has been one of the clearest voices leading the call for climate action based on the facts in the last few decades. He is a physicist and a physical oceanographer. And back in 2015, when everyone was talking about a record hot planet, Stefan and his colleagues published a seminal paper in Nature about a cold blob in the Atlantic Ocean. It argued that a southern branch of the Gulf Stream, so familiar to all of us here in Ireland, it's the reason we can swim in the west of Ireland, known as the AMOC, had weakened by 15% in the recent decades, which is unprecedented in over 1,000 years, if not 1,600 years. The implications of this are absolutely immense. Stefan previously worked in New Zealand and also at the Institute of Marine Science in Kiel, Germany, where he did his PhD. He has advised the German government as a member of its advisory council, and he was one of the lead authors of the IPCC Fourth Assessment Report back in 2007. And why is he here? Well, as any of you who've attended these talks will know, the EPA seeks to hear from outstanding and leading scientists in their field. And Stefan is indeed one of those people. He's been listed as one of the world's leading climate scientists and is among the most cited in climate science literature. So we are very, very happy to have him here this evening. And perhaps most importantly for all of us in the public, non-scientists, he is a highly regarded scientific communicator, winning the Climate Communication Prize of the American Geophysical Union in 2017. And he's also co-founded initiatives that seek to enhance the public understanding of climate science. So we're here to listen, and after his talk, we will have an informal Q&A conversation with him, and I hope you will all get involved in that. For those of you here in the Mansion House, just raise your hand and we will have a microphone come towards you. For those of you online, please can you use the comments section in YouTube to put your questions in. And comments and questions, the more the merrier. I just ask if you would mind to keep them concise and brief so we can include as many people as possible. So just note the emergency exits, everyone here in the Mansion House. The evacuation assembly point is St. Anne's Church on Dawson Street. Please, if you can, remain seated for the lecture. And can I ask you all just to dig your hands into your pockets or bags and look at your phone to make sure it is on silent. Thank you very much. This event is being recorded by the EPA for use on their social media channels, and it will be released onto YouTube afterwards. If you're using social media with your silent phones, please use the hashtag ClimateLecture2023. But first, I'm delighted to welcome Laura Burke, Director General of the EPA, who's going to say a few words. Laura.
Good evening, and absolutely delighted to be here, and you're all welcome to the first of our climate lectures for 2023. And I'm also really delighted that we're doing this lecture in partnership with Dublin City Council. So to welcome all of you here, and of course the Lord Mayor as well, delighted that she can attend this evening. So we are once again in the Mansion House, a great place to be and I suppose well associated with EPA lectures over the years. And you know, Ella was highlighting the expertise of our speaker, and maybe to take a step back for a moment and remember the findings of the most recent IPCC report, which are clear, they're stark, and they are challenging. They reinforce the urgent need for action to reduce greenhouse gas emissions whilst adapting to current and future impacts of climate change, because the impacts are already with us. And here in Ireland, among the key findings of the EPA's Climate Change in the Irish Mind are that 85% of Irish people are worried about climate change, and nearly half of people think they are being harmed right now by climate change. And 95% believe that future generations of people will be harmed. So we've got a population in Ireland that understand the implications of climate change. They understand that it's happening. And unlike other countries, there really is a very, very small proportion of people that are skeptical. So what we have now is a population and a people that all of us recognize the need to transition to climate neutrality and resilience. And people see the benefits for themselves as well as Ireland in general in moving to carbon neutrality, and many people are actually well advanced along that journey. So we're in a good spot in the I suppose the thinking on climate change. Where we need to move to now is on action. And this long-running lecture series, as Ella has highlighted, presents some of the world's most leading climate scientists, decision makers, influencers, to encourage and provide opportunities for a wider public discussion on climate action. And it's great to see so many kind of familiar faces. I suppose the lectures over the years, you get to know people who are in the audience, and there's many familiar faces here tonight. But it is wonderful in this kind of, I suppose, new reality that we can have the hybrid format as well, with people, as Ella said, joining from not only from Ireland, but right across the world. And our speaker tonight is both internationally renowned for his scientific endeavours, but also skilled climate science communicator. And Professor Rahmstorf, I'm so happy, and we really appreciate you coming to Ireland and coming to Dublin for this lecture. I think, you know, maybe during the COVID period, I don't think it was only me, you can watch things online, and it's great that we've got people available online, but it's great actually to be here physically with you giving this lecture to us. And Ella, of course, we're delighted that you have agreed to chair this evening's session. And as an island nation on the edge of the Atlantic Ocean, Ireland is especially exposed to climate-driven changes in the North Atlantic. Our mild winters are caused by the warming effect of the Gulf Stream. Our biodiversity, our society, our economy are all shaped by the temperate oceanic climate. From the rich ecosystems we find around our coasts, to our food systems, our marine economy, cultural heritage, and even our planned offshore renewable energy projects, the importance of the Gulf Stream to Ireland is clear to see. The status of Ireland's climate report, published in 2020, highlighted that global warming has resulted in Ireland's climate becoming warmer and wetter. Sea level rise, increased ocean acidity, and higher ocean temperatures are also observed in our oceans and coastal areas. And Ireland's ocean and terrestrial ecosystems are responding to these changes, resulting in changes in ocean species and lower growing season on land. Understanding the evolution of climate change and the ocean is essential if we are to understand our future. This knowledge can help inform policy to manage our responses and adapt to the future climate conditions that we will be inevitably exposed to. And in the context of moving from science to action, I'm also really looking forward to hearing Professor Rahmstorf discuss the impact of disinformation and fake news, and his hope that we are reaching a positive social tipping point for climate action. The publication of the IPCC's sixth assessment report illustrates the importance of robust climate science. The EPA is leading the development of Ireland's first climate change assessment based on scientific research and analysis and observations in Ireland, and that will be published later this year. It's going to build on and localise information from the sixth assessment cycle, including the recent synthesis report, all with the aim to better inform our national conversation on climate action. So in conclusion, thank you all again for being here tonight. The lecture will be uploaded onto the EPA website, our YouTube channel, and also for the first time, it's going to be available to listen back to as a podcast. So whatever your preferred means of hearing the lecture, we have it available for you. So look, thank you all again for joining us, whether it be in person or online, and I look forward to the lecture. Thank you very much.
Laura, thank you so much for that. And important, obviously, to emphasise understanding the consequences of climate breakdown and the vital need to ensure the integrity of the information which informs our collective discussions on climate action, and something we will hopefully have time to discuss afterwards. But I'm delighted now to introduce Professor Stefan Rahmstorf, whose talk is entitled Ocean Circulation, Tipping Points and the Public Climate Debate. Stefan.
Yeah, thanks very much for the nice introduction. I'm delighted to be here in Dublin. It's actually the second time I'm in Ireland in my life. I'm almost ashamed to say that I have waited since 1981 until now to come back to Ireland. In 1981, I arrived from Holyhead in Dunleary with my girlfriend, backpacking and camping. And it was wonderful, and I haven't been back since. So it's great to be here again. And I will talk about ocean circulation, tipping points, and the public climate debate. There's actually 3 topics and 3 parts of my talk, but they are all interlinked. And I begin with a historic quote that I like showing by the famous explorer, scientist Alexander von Humboldt from Berlin. I actually went myself to an Alexander von Humboldt high school, and my kids do that as well now, although in a different city. But he is one of the most famous German natural scientists of the 19th century. And he wrote already in 1843 that humans are changing the climate, quote, by cutting down forests and by releasing large amounts of steam and gas at the centers of industry. So like in many other things, Humboldt was a bit ahead of his time at the time, but not that much. It was was just in the decade after that that Eunice Foote and John Tyndall discovered the effect of CO2 causing the greenhouse effect and so on. By now we have quite a detailed understanding of how the climate system works, of the physics, but also climate history. And I like to point out before I launch into the ocean circulation issue that we are leaving the Holocene. This is the global temperature since the last ice age, which ended about 20,000 years ago. And the transition into the Holocene. At the beginning of the Holocene, we, Homo sapiens, discovered agriculture, became settled, started to build cities, and have benefited for the last 10,000 years from a very stable climate. But we have left it already. The temperature now is already higher than any time in the Holocene in the last 10,000 years. And so you have to go back more than 100,000 years into the Eemian interglacial to find an Earth that is probably slightly warmer still than we are now. I hope you all know that these ice age cycles are caused by Earth orbital cycles, the so-called Milankovitch cycles that was worked out in the 1920s and well established by the 1950s. I actually learned that in school in geography lessons. But we now have not only these data, but also the climate model that we're running at our institute is able to reproduce all the ice ages of the last 3 million years based on these Earth orbital cycles, which can be calculated with astronomical precision millions of years back and into the future. In case you're wondering, the next ice age would normally be due in about 50,000 years from now, but the CO2 emissions that we have already caused have probably already prevented that, because CO2 will linger for tens of thousands of years in the atmosphere elevated, because it takes such a long time to finally put it down into the deep sea, into the sediments again. So not only the climate is warming in the atmosphere at the Earth's surface, but also in the oceans. And in fact, if you look at the energy budget of the planet that we have changed by our increase of greenhouse gas concentrations in the atmosphere, then 93% of the extra heat trapped by the greenhouse gases is actually ending up in the oceans. Not, of course, because the oceans have warmed more than the atmosphere. They have not. They have warmed less than the atmosphere, but they have a much, much bigger heat capacity, and that's why it takes so much heat energy to warm up the oceans, and that's why most of that has actually gone into warming the oceans. Now, such a major warming of our oceans will have also effects on the ocean circulation, and that is the first part of my talk. It will talk about the changes in the so-called Atlantic overturning circulation, which is shown in a very simplified cartoon figure here, with the warm surface waters in red flowing northward throughout the Atlantic. The water then sinking down into the depth in the northern Atlantic, in the region around Greenland and the Nordic seas, and then return as a cold current in about 2,000 meters depth to the south. And of course that works like a central heating system, transports a huge amount of heat towards the northern Atlantic, which is released to the atmosphere there, and is responsible then for the relatively mild climate of Ireland, of Great Britain in general, and large parts of northwestern Europe, because we typically get our weather from the west, from the Atlantic in the mid-latitudes, and there it passes over ocean that is much warmer than in the North Pacific, for example. Just for the terminology, the Gulf Stream is the part of this surface current that flows up along Florida and along the American coast until at Cape Hatteras it leaves the American coastline and crosses the Atlantic and towards Ireland. But that is, that's kind of part of that Atlantic overturning circulation that I am speaking about. And at the same time, the Atlantic overturning forms part of the Gulf Stream, because the Gulf Stream also has actually the larger part that is wind-driven and is recirculating on the eastern side of the Atlantic at the surface as part of a horizontal gyre circulation. That doesn't do much heat transport, because that water returns at the surface at a similar temperature as it has flowed north in the Gulf Stream. The real big thing for climate, for the temperature, is that fraction of the Gulf Stream water that really goes down into the deep ocean in the high latitude North Atlantic, because that has a big temperature difference compared to the surface water, and the heat transport, of course, is the temperature difference between that warm northward flow and the cold southward flow times the volume transport of that flow. So I'm not using the term Gulf Stream, although in the public mind this is probably what I'm talking about, but I'm talking about, I'm calling it Atlantic overturning circulation or Atlantic meridional overturning circulation. Meridional means in north-south direction, or in short, AMOC, A-M-O-C. Now, there was a nice New York Times article a couple of years ago which had beautiful illustrations, all interactive, online, and it was talking about dramatic dangers due to changes in this current. And that actually was a very good article. It was evaluated by a project called Climate Feedback, which is a very good initiative which evaluates scientific information on climate appearing in the popular media by asking a number of scientists who are working in this particular field covered by that article to evaluate the accuracy of media articles, and this was evaluated very highly. So a little advertisement for Climate Feedback. They've now become bigger. They're called Science Feedback, and they're also, since the corona pandemic, evaluating health articles in popular media. Here's another view. I think this is from NASA. Also, it's actually a snapshot from an animation video that you can find online from NASA about this circulation, which shows a little bit more detail compared to the very simple cartoon image that I showed before. And even that is still much too simplified. I'll show you a model simulation later on where you see how turbulent and full of eddies the flow in reality is. It's not just such a straight line as is depicted in these simplified images. The whole thing in the Atlantic is just part of a worldwide global overturning circulation. And yeah, you see again in the Atlantic the warm northward current in red and the North Atlantic deep water returning in blue to the south, but you see an additional component coming from Antarctica. And actually that's the purple water, the Antarctic bottom water. I will also mention that later in my talk. And the orange dots, they are the so-called deep water formation areas where the water sinks down to the depth. And why does it sink down? Because these are the parts of the surface ocean where the waters have the highest density. And if the water is very dense, it's heavier than the water below and can sink down. And that deep water then fills the deep ocean. And it's very dense and sits there. And so you might wonder, why doesn't it then, once that has happened once, all sit there and stagnates and there's no overturning? That's because all the turbulence in the ocean slowly diffuses heat downwards, and thereby warming the deeper waters, thereby they get less dense, and the surface waters near the poles are then dense and cold enough again to replace that. And so that's typically what you would also get if you have a water basin and you heat it on one side, cool it on the other side. We typically show that on the Open Science Day. It's a famous instrument, the Rahmstorf instrument from the early 20th century. And this overturning has an incredibly important role for marine life because on one hand, it does what we call ventilate the ocean. That actually means that it replenishes it with oxygen, because that is, marine life uses up the oxygen at the depth, by decaying organic matter, etc. And the oxygen is replenished at the surface with a gas exchange between atmosphere and ocean, and then oxygen, the water that sinks down, is oxygen rich. At the same time, if water sinks down in part of the ocean, it has to come up somewhere else again. So it has to replace other water that gets pushed up by that. That's a pretty diffuse process that happens all over the ocean. And that actually brings up nutrients back to the surface, which normally would slowly sink down, or they do slowly sink down, but then the upwelling of that water brings them back up. Because for marine life, it's rather different from what we know from land. On land, we know the plants, they need water. Water is maybe not in Ireland, but in some parts of the world, it's precious and there's not enough. Or they are fighting for sunlight, and that's why trees grow high to win against lower plants, get more of the sun. But in the ocean, there is no lack of water, obviously, but the really rare stuff is the nutrients because they sink down. And so you can only do photosynthesis in the surface layer where there's sunlight, but the nutrients, they all drop down, be it dead algae or fecal pellets or dead fish. Everything that is dead eventually sinks down because it's heavier than water. And so a lot of the ocean is depleted of nutrients. It's a real limiting factor. And that's why it's so important to have an overturning so that the water just doesn't sit there stagnant and grow kind of oxygen depleted and old, etc. We need this continual replenishment, overturning of the ocean for marine life. Now, if you look at the latest IPCC report and look what does it project for the year 2100, you find one panel high warming projection of the more sensitive model group for a moderate emission scenario, and it looks like this. They predict that the whole globe warms until the year 2100, except this cold blob in the North Atlantic. And when we zoom in here, this is why I really wanted to talk about this when I was invited to Dublin, because Ireland here is actually predicted to be cooling by the year 2100. It's a subset of models, that's not all models, but this is highly significant. And so I think this is the best place really to talk about a slowdown of the Atlantic overturning circulation, which is actually behind this, as I will show you in the next minutes. Now, this is not zooming out to the same thing. This is not a model forecast. This is the observations of the surface temperature change since the second half of the 19th century. And here again, you see practically the entire globe has warmed, of course, everyone knows that, but there is this big exception in the northern Atlantic, which has actually cooled in the last more than 100 years. And if we just look at a more recent time period since the satellite era, that is time series or trend since the year 1993 from the Copernicus satellite system, you see this very clearly, that this region south of Greenland and Iceland and to the west of Ireland has actually cooled also in the last decades. And there are more images that show the same phenomenon in this paper. In 2015, we had this diagram which showed a linear trend since 1900, showing a very similar thing. And the picture on the top right here, that actually is an analysis of ocean heat content down to 2,000 meters. So it's the upper 2,000 meters of ocean. And starting in 1958, this one. And again, you see the Northern Atlantic is the one region that has cooled most in that period in the ocean down to 2,000 meters depth. So we're not just talking about some kind of surface phenomenon maybe caused by surface heat exchange. We're talking about real deep ocean phenomenon here. Now, what causes that? In order to understand that, we can turn to climate models, and here I show you from the Geophysical Fluid Dynamics Laboratory in Princeton in the USA, a beautiful climate model simulation. This is the ocean component of a coupled climate model, and now you see a beautiful picture of the Gulf Stream as this red current coming up the coast of Florida, coming out of the Gulf of Mexico. That's why it's called the Gulf Stream. And at Cape Hatteras, it leaves the US coast. From there on, you find inshore this blue colder water mass that has come down from the north, from the Labrador Sea. This is a model simulation, but it all looks very much like the reality. If you look at satellite images, you'd see a very similar thing. You can find this animation here on the internet. And at YouTube, and you also see that after the Gulf Stream leaves the American coast, it starts to meander, it becomes unstable dynamically. It's not a very straight line, but it actually continues right across the northern Atlantic and on into the Nordic seas and past Ireland, Scotland, and so on. Now, when you take this model and you increase the CO2 concentration in the atmosphere, what happens to the sea surface temperatures? That is shown here in this Earth. The sea surface temperature cools south of Greenland, and I should add, we have subtracted for this image the global mean sea surface temperature change. So we have subtracted the average global warming out of it, because if you add CO2, obviously the whole ocean warms, but we subtracted the average warming. So everything which is blue has either cooled or just warmed less than the average, and everything that is orange has warmed more than average. And now again, you see that cooling or below average warming south of Greenland, but you see an additional very fascinating thing, namely this excessive warming along the North American coast. And the interesting thing is that this is also due to a slowdown of the AMOC. And there are dynamic reasons for this. They're a bit hard to explain, except to oceanography students, because it has to do with vorticity conservation on a rotating sphere, but it's a well understood physical phenomenon that at the point where this deep water flow coming from those deep water formation areas south of Greenland, that where this crosses under the Gulf Stream. So you have the southward deep flow crossing under the Gulf Stream, or maybe more easy to understand, the Gulf Stream crossing over that southward deep flow. And for reasons of vorticity conservation, which has to do with angular momentum for the physicists, when this slows down, when the deep current slows down, it makes the Gulf Stream move closer inshore. And you can see that south of that orange part, there is a blue part, which has cooled. So this really is an indication that the warm Gulf Stream waters have shifted somewhat northward and closer to the American coastline here. And so this is now we have a kind of a fingerprint pattern of a slowdown of the AMOC, which consists of this blue patch and the orange part along the American coast. And my PhD student, Levke Cesar, which afterwards did her postdoc here in Ireland, she calculated the trend of the observed sea surface temperature since 1900 based on ship measurements. That's why it's a kind of a bit out of focus picture, because ships are not crisscrossing the ocean since 1900 every year, everywhere. So you have to average, etc., and smooth that. But I think you can see in the observations this fingerprint pattern, including the blue south of Greenland and that orange part along the North American coast. And by calibrating this fingerprint that we see in the observed changes with what we know from modeling, we concluded that this pattern corresponds to about 15% slowdown of the AMOC, of that Atlantic meridional overturning circulation. This 15% weakening actually roughly corresponds to 15 times the flow of the Amazon River, which is the largest river on Earth. So just this 15% weakening already is a huge amount of water and a really big amount of heat transport. And it's this reduced heat transport, of course, which causes that blue blob there, the cold blob south of Greenland, because that overturning circulation now transports less heat into that area than it used to. I showed you this for one model, this very nicely high-resolution GFDL model, but just to convince you that this is a general phenomenon, I show you here the average of all the so-called CMIP6 models. That is the current generation of coupled climate models that was run for the IPCC report by more than 20 centers around the world that have their own climate models, and that is the average. And here what you see is kind of a joint correlation pattern between the changes in the AMOC, which is shown on the right-hand side. In the model, we know what the AMOC is doing, of course, unlike in the real world, for lack of measurements. But in the models, we know exactly what happens, and we see here this blue thing shows a slowdown of the AMOC. This is a vertical section, streamlines. And on the left picture, you see the change in sea surface temperatures, and you see the less warming than in the global average south of Greenland there. That light yellow shows that there has been less warming there. It's historic simulations, so the last 100 years in the climate models, driven by the observed CO2 changes and other greenhouse gas changes, aerosol changes. And you also see this kind of darker red along the American coast. So even these models that are more coarse resolution than the one I showed you earlier show a similar phenomenon there with that fingerprint pattern. And in these models, we know it is due to the AMOC slowdown because it's correlated directly with the AMOC. And because it's a model average over many models, we know it's not some natural internal variability because that would average out between all the different models. And what you get in a model average is the part that is forced by changes in greenhouse gases and so on. So that just confirms that this idea of a fingerprint, of a slowdown of the AMOC is robust and actually driven by forcing and not by some random internal variability, natural variability in the system. Now let's look again at the satellite data from the Copernicus satellites. This is a global picture of the sea surface temperature trend since 1993. I actually only recently, by chance, preparing a talk in Rome that I gave a couple of weeks ago, discovered this picture. And I was quite stunned when zooming into it. You don't just see that cold blob, but of course you also see that red area along the American coast, but just running along the south of it, you see quite a bit of white, which indicates that indeed also in the satellite you see that northward shift of the Gulf Stream. So again, this fingerprint pattern plus that indication of a shift, which in the shipboard observations it's too subtle and there's not enough continuous observations to really see this, but the satellites, they show it. We can also look further back in time. I think I only very briefly mentioned that we don't know how strong the overturning is from measurements because there are no measurements except the ones from the RAPID project, but that only started in 2004, if I remember correctly now. Yeah, I think it's 2004. So very recent, too short for a real climate analysis. And so we don't really know further back in time how this overturning system, the AMOC, has changed. But you can reconstruct it to some extent from sediment data. And the map inset on the top right shows the locations of all the sediments that were used in several studies that we just compiled here. They're all studies by independent groups of paleoclimatologists with rather different methods to reconstruct the changes in the AMOC. And yeah, you see that the different curves, if you just look at the left-hand column there for now, the different curves, they all have one thing in common. There's, of course, a lot of noise and there's uncertainty in these proxy data reconstructions, but they all have in common that there is a downward trend in the last 100 years or so. And the top one, the dark blue one, is actually from our paper in 2015, where we worked with Michael Mann and others to reconstruct the AMOC based on temperature changes, like these sea surface temperature changes in the fingerprint that I showed you, although it was only actually looking at the cold blob temperature changes, and we reconstructed the AMOC based on that. The light blue curve at the end is from the instrumental data with the same method, but including, yeah, it's actually the same method. It is based on the sea surface temperature in the cold blob. But the other further below that are always compared with those same one in the top panel are different reconstructions One, for example, based on the grain size of the sediments in the deep Atlantic, where the North Atlantic deep water flows over, because currents tend to sort grains depending on how strong the current is. You know this from a beach. If you have a beach with low energy, little wave activity, little tidal currents going over the beach at high tide, then you get fine-grained sand, and if you have a very high-energy environment, you get coarse-grained because the fine grains are just washed away. And the same happens at the ocean bottom in 2,000 meters depth, and you can reconstruct a strength of the North Atlantic deepwater flow there based on the grain size in the sediments. When you drill down, you travel back in time because they build up over thousands of years, these sediments, and you can reconstruct the AMOC strength. That's just one method of several different methods. The point here is that with paleoclimate proxy data, that's always very important that you have several independent lines of evidence, of methods that come to the same results before you really start to believe it's robust. And these data, they all agree that the Atlantic overturning circulation now in recent decades is probably the weakest in the last millennium. That actually fits what is expected because the climate models, they all predict a weakening of the AMOC in response to global warming. And so in a way, what we find here is like an upside-down hockey stick. We know from the temperature reconstructions that they have this hockey stick shape. The modern warming really sticks out. I showed you one of the latest ones early on in this talk. Modern warming really stands out, has come after a very stable period of climate, and therefore what you expect is the AMOC to weaken, and before it shouldn't have changed very much, and this is exactly what the paleoclimatic proxy data show. On the right-hand panel, you just see a zoom into the last 100 years, since 1900, and you see that the reconstruction that my PhD student Levke did is a light blue curve on the top there on the right-hand column. It shows actually a weakening down to about 1990 and then a recovery in the early 2000s, and then it goes down again, so some multi-decadal variability. And it's quite interesting to, and there has been a bit of a debate in the literature whether this tail end of that reconstruction agrees with other methods of trying to reconstruct the overturning circulation. Now, the first thing on the top there is this RAPID project that I mentioned that measures since 2004 with a big array of moorings in the Atlantic across the Gulf Stream, the extent of the overturning. Then there are other attempts to use climate models with data assimilation, where you have different sets of data that you force the climate model to follow along in order to also recover internal variability, which otherwise would be random if it's not forced. And you see Levke Cesar's reconstruction there and several others from sediment data. And I would say, by and large, within the uncertainties, they all show a pretty similar evolution over the last few decades. So that kind of raises our confidence that these methods actually provide reliable results here. Now, I haven't really talked about the reasons for the weakening of the overturning yet. I have tried to argue here, tried to convince you that there is a weakening that is shown clearly in these temperature patterns, but also other data. But what is the reason? Now, there could be two reasons, because this is a density-driven flow and the water has to be heavy to sink down into the deep ocean. If you reduce the density of the surface water, you will reduce that sinking motion and the whole overturning. And there is two ways to reduce the density of ocean water. One is to warm it up, and the other one is to add fresh water, that is, reduce the salt content, what we call salinity. And obviously, the more saline the water is, the denser it is. And There are therefore two possible factors why global warming would weaken this current. Number one, it could warm the surface ocean. And now you would say, but wow, in the critical region where it should sink down, it has actually cooled. So that can't be the reason, or can't be, certainly not the whole reason here. But the second factor is that if you add a lot of fresh water, you reduce the salt content, the salinity, and that is indeed observed. The salinity in this North Atlantic region has gone down. And how do you do that? Either by rainfall, increased rainfall. That is a big part of that, probably the main part, because in a warming Earth, the normal water cycle gets enhanced. That is, there's more evaporation, especially in the subtropics, and therefore, where there's more evaporation, more rain has to come down, and in the higher latitudes, you typically have net rainfall amounts, and they increase with global warming. And so this added rainfall dilutes the ocean surface, slows down the AMOC. But in this image, you also see a big ice sheet there, the Greenland ice sheet, right next to where the deep water forms. And the Greenland ice sheet is also releasing a lot of fresh water by melting. That's another fact that the satellites show. The Greenland ice sheet is increasingly losing ice mass due to melting, and that meltwater enters the northern Atlantic, and it dilutes the salinity, slows down the AMOC. Little side comment, when people hear cold meltwater is coming down from Greenland, they often think, well, isn't that cold blob maybe just cold because the cold water coming down from Greenland makes it cold? That is actually not the case if you do the sums, the calculation. That cold water doesn't have much of a cooling effect because the northern Atlantic there is pretty cold anyway. And if you just look at the amounts, the difference between the actual temperature of the water that's already there and the Greenland meltwater is not so large, but the difference between the salinity of the ocean water and the Greenland meltwater is huge, because the Greenland meltwater has practically zero salinity. This ice sheet, of course, is formed by snowfall, and therefore that's not salt water that is coming down there. And so meltwater is part of the explanation for the cold blob, but not because the meltwater is cold, but because the meltwater is fresh, and therefore it has a slowdown effect on the AMOC, and the AMOC brings less heat to the north, and therefore there's this cooling. This is all, you know, the climate models, of course, they calculate this quantitatively, etc. So you really know that that is the case, and the coldness of the meltwater is not very relevant at all. Okay, now I hope I have shown you the AMOC is slowing down, and I have shown you what the reasons are. And it is as predicted by the climate models. There's another climate model prediction come true. And now I want to talk a little bit, what many people often ask is, what are the consequences? And who of you has seen The Day After Tomorrow, that Hollywood movie? A few hands are going up. Yeah, quite a few hands are going up. Then you probably have the idea, breakdown of the AMOC. Actually, they don't call it Gulf Stream. It's very good in this movie. So it has many good aspects. I actually wrote a review for New Scientist at the time the movie came out, and I praised many aspects of it. And where they really deviate from physics drastically, there are a few. One of them is a time scale. I talked to the screenwriter Jeffrey Nachmanoff about this when we did a joint event about this film, and so I chatted with him, also with the director, Roland Emmerich, and Jeffrey said, look, if we were making films for a few million people, we'd stick to the laws of physics. We are in the business of making films for a few 100 million people, and there we stick to the laws of Hollywood. And so that's why there are some absolutely unphysical things there in the movie, like cold air coming down and shock freezing people that kind of fall dead out of a helicopter. If you bring cold air down from the upper troposphere, it warms up because pressure increases. There's no way it arrives cold. So that's one of the things. They also have a conveyor belt diagram that runs the wrong way around in the movie. So there's a few problems. But let me get back to this. So if you have seen this movie, you think, oh God, Europe freezes. So you'll be really surprised to find that the cold blob out there in the Atlantic causes heat waves in Europe. This is shown by a study by Aurélie Duchesse and colleagues in Britain. And it actually makes sense once you think about it, because you see the actual cold blob. I showed you many pictures of it now. It's over the ocean. It's not over the land. You don't have any cooling over the land yet, unless that really gets bigger because we slow down the AMOC a lot further. But we have cold water out over the Atlantic there, and that affects the pressure patterns. It tends to have a low pressure above it, which is shown in the right-hand picture there in blue. It's basically a big low pressure that likes to linger over that cold water. And that goes, of course, the air goes anti-clockwise around a low-pressure system. And that's why, as shown in the red arrow, we get air from the southwest into Europe more often than normal with this cold blob out there. And, you know, if air comes from the southwest, it's warm air. And that's why actually Europe, there's one reason why Europe is a real hotspot of heat waves. I was in Britain actually last summer when London had more than 40 degrees for the first time in history. But I was up in Scotland swimming in the North Sea, which had 10 degrees water temperature. Anyway, so somewhat for the general audience, counterintuitive result, cold blob out in the Atlantic causes excessive heat waves in Europe. There's more increase in heat wave activity here in Europe than other regions on the same latitude in the mid-latitudes. Now, a further consequence that has been studied, that previous one was actually just data analysis. Now, this is a modeling study looking at how in the future with further AMOC weakening, the storm activity would change, and this study finds increased winter storms, westerlies, when the AMOC slows down across Britain, basically, and even into Germany and Denmark here. So there are a few studies that look at potential consequences. There is a lot more to say about this, about the biological side, for example, if you slow down the AMOC, the effect on nutrients, marine biology, but it's largely unexplored. We tried to get a research project funded on this with a European context with colleagues from Iceland, Scandinavia, etc., but didn't get it funded. So this is something that needs more research, how the marine life will be impacted by an AMOC slowdown. Here is another study. This one now shows a global warming scenario where the AMOC collapses. This typically doesn't happen in models. This is why the IPCC wrote that it's unlikely by the year 2100 to break down altogether, although all the models show a weakening of the AMOC by 2100 of different degrees, just very little up to 50% weakening. But here's a model simulation that actually got a collapse of the AMOC due to a standard global warming run. And what did they do differently? They corrected for salinity errors in the model with using observed salinity data, because we're talking here about subtle density differences driving this flow. So if the model doesn't get all the distribution of salinity across the whole Atlantic, including down to the depth, exactly right, then the results of models may be wrong, and there are good reasons why the models are not getting salinity right, because it's very hard to get regional precipitation right. This is one of the most difficult things in climate modeling. Never trust details of regional precipitation changes in models, because you easily shift the weather system, precipitation systems by a few hundred kilometers north or south or so. And so the freshwater budget of the Atlantic is very difficult to get right, which is one reason why I have actually worked since 1991 on this problem, and we haven't really made huge progress in really nailing this down and reducing the uncertainties. But what these people did is they used observational data to tweak the salinity in the Atlantic rather than letting the model freely do it itself. And they found after they made it more realistic in the terms of salinity distribution, the model became much more sensitive to global warming and the AMOC collapsed. And the consequence of that is shown on the right-hand panel here in the winter. Now you are not getting just a very slight cooling like in that IPCC diagram that I showed earlier on, but you get actually a massive cooling in the northern Atlantic, including across Britain, etc. That would be a really drastic scenario. And yeah, it is certainly possible. One other factor actually why many climate models probably underestimate the weakening of the AMOC is that they mostly don't have an interactive Greenland ice sheet, which actually dumps a lot of meltwater into the North Atlantic. And so probably what the IPCC finds in the standard model runs is an underestimation of the real problem. Now, when we're talking about a shutdown of the AMOC, there's not only consequences on the temperature, but for example, on sea level. We investigate this. This was one of my postdocs, Anders Levermann, at the time, 2005. In a study, we looked at what happens to sea level when the AMOC shuts down in a global climate model. And you get quite a big effect here. These numbers are in meters. And so the kind of darker orange tones, they get 1 meter sea level rise in addition to the global sea level rise that's happening anyway for ice melt and warming. But this is just a redistribution of the seawater because of the changing ocean currents. It's because ocean circulation always comes with a slope in sea level because of the Coriolis force. So the sea level is not flat horizontal like in your bathtub. It is inclined depending on the currents. It's a standard method how you actually measure currents from ships by looking at as you go further down how the slopes change because the flow is in balance with the Coriolis force. And that is why when you change the flow by shutting down the AMOC, you change the sea level massively, especially around the North Atlantic. You get an increase, whereas in the southern hemisphere, the sea level would drop in response. So especially for Europe, this would be a big problem along the coastlines if we shut down the AMOC, not just a cooling problem, but also a massive sea level rise problem. Now, when I talk about shutdown, I'm already kind of talking about a tipping point. And so it's time to go to the part of my talk about tipping points here, because you probably have read the term tipping points a lot in the media, but not necessarily know exactly what it means. And this is a nice diagram where I don't actually know what the source is, but it, apart from being fancy, it also illustrates what a tipping point is by showing a ball that is sitting in a bowl. And so if this person here pushes it a little bit over to the side, it will roll back to that minimum here, to that hollow, because that's a stable equilibrium. And so you can perturb that and it will go back by itself, unless you push it over that bump here. Then it's not going to roll back anymore. It's going to roll into the fire there. And that point is the tipping point. The point on the top there of that hill is the tipping point. And the tipping point means that from then on, you don't have to push anymore. This system will keep changing by itself and without any further forcing, what we call, like without further CO2 emissions, for example. That system would then change by itself into a completely different state. And this is what a tipping point is in the climate system. And since you can see from this is not really rocket science, it's not a complicated physics that you need for a tipping point. And so it's plausible that all over the climate system, you find systems, subsystems that behave like this and have their tipping points. And so this is one version of what's a tipping point. There are different kind of funny versions, entertaining versions about tipping points on the internet that you can find. But it's a serious issue. We wrote a commentary on this in Nature just a few years ago, 2019, where we pointed out the various tipping points that you see here on the side, on the left-hand side from you. And that includes the Greenland ice sheet. The ice sheets have their own tipping points. The Amazon rainforest, so biological systems have their tipping points, like the coral reefs. They're probably past their tipping point. Majority of the Great Barrier Reef in Australia has already bleached in the last years, for example. This is a very sad thing. And you also see these arrows here that indicate that the tipping points can interact. They can, if one tips, they can flip over the next one like dominoes. And for example, if the Greenland ice sheet is across its tipping point, it will just melt until it's completely gone without any further warming. You don't, beyond the tipping point of the Greenland ice sheet, you don't need to warm the climate any further. It's then doomed to melt down altogether. That alone brings 7 meters global sea level rise, by the way. And it's luckily not going to happen within 50 years or 100 years. It will take probably more like 1,000 years until it's completely gone. But we may already passing the tipping point now. We wouldn't even be sure because it's such a slow responding system that you couldn't easily tell whether it's past its tipping point. Because nothing changes in that moment. It's just that from then on, the whole rest of the evolution is like a vicious cycle just happening by itself. So if the Greenland ice sheet melts, that dumps fresh water into the Atlantic, it could bring the AMOC across its tipping point. The AMOC then could trigger droughts in the Amazon region because when the AMOC breaks down, this changes the heat balance between the northern and the southern hemisphere, namely the northern hemisphere cools, the southern hemisphere warms. Due to that, that shifts the tropical rainfall belts, and so the Amazon wouldn't be right under the tropical rainfall belt anymore, and so on. So we concluded that the biggest kind of nightmare, basically, I would call it, from climate scientists, is a cascade of tipping points where the system really gets out of control. Now here is a more recent review paper by David Armstrong McKay and colleagues. I was not involved in that one, but it tries to estimate at what temperature range you trigger various tipping points in the climate system, and the dark red ones are actually between 1.5 and 2.0 degrees Celsius. That is quite a shocking result because really we always considered these things low probability, high impact events and probably only happening after a lot of global warming, not already below 2 degrees. But now there are several candidates of tipping points which could already be crossed even below 2 degrees of warming. The IPCC synthesis report, that was actually all, IPCC of course was before that study that I just showed because it was too recent for the IPCC deadline, but the IPCC concluded in its headline statements that abrupt and or irreversible changes in the climate system, including changes triggered when tipping points are reached, increase with further global warming with high confidence. Now you might say, yeah, sure, they increase, but how much? The IPCC report, synthesis report, also in the further text explains a little bit more quantitatively, namely that there is a transition from moderate risk to high risk of crossing tipping points in a global warming region between 1.5 and 2.5 degrees. So this is really serious. This is very strong reasons to try our very best to limit warming to 1.5 degrees. If we want to avoid getting into the high-risk area of crossing tipping points. Now a little bit more about the AMOC tipping point. I have already mentioned, of course, that the AMOC has a tipping point, but why? The reason is tipping points always come with self-reinforcing feedbacks. I could explain it to you for the ice sheets, etc., but I don't have the time. I will just explain the AMOC one. And with the AMOC, you already know that the water needs to be saline in order to sink down. But then why is the water in the northern Atlantic especially saline? It's because you have the AMOC bringing water from the subtropics, which have high salinities because of strong evaporation in the subtropics. This subtropical waters is transported north to these deep water formation regions by the AMOC. And so you have an AMOC because the water is saline, and the water is saline because you have the AMOC. That is a self-reinforcing feedback. And that, if you dilute the water too much with fresh water, you reach a tipping point where that feedback works the other way around. The water is now fresh, the AMOC weakens. It gets even fresher because the AMOC weakens and brings less salty waters. The AMOC gets even more weak, and then you have a self-reinforcing vicious cycle that brings the AMOC to collapse. And this is a schematic diagram showing the stability diagram, where on the horizontal axis is shown how much fresh water goes into the North Atlantic. It's measured in a unit Sverdrups here. That's one Amazon river is 0.2 Sverdrups. A Sverdrup is 1 million cubic meter per second. And on the vertical axis, you see the strength of that North Atlantic deepwater flow, i.e. the AMOC. And so a stable AMOC is on the green line. That's an equilibrium state. And you see the present climate is with question marks somewhere on that upper branch where we have an AMOC, about 17 Sverdrup flow. But if you add fresh water, you move to the right on that diagram until you hit that point where the curve bends back on itself. This curve actually is the solution of a quadratic. You get a parabola lying on the side here. When you do this kind of more salt, more AMOC, etc., you come up with a quadratic equation as a solution in the most simple case, and that's why you get this shape. And when you go beyond that bifurcation point, that is a tipping point. Beyond that, you have no more stable state, and the AMOC will collapse. Like the arrows show, it will fall down onto that lower branch with a switched off AMOC. To get it back, it's not enough to go just back to that point under the stomal bifurcation to the left. You have to go much further to the left to another tipping point where it kickstarts again. But we're never going to get back, not in hundreds of years when we shut the AMOC down. This is not fantasy. This is actually first shown in 1961 by famous American oceanographer Henry Stommel, this basic structure in a very simple model. But we did, in 2005, we published a model intercomparison between a lot of climate models. The top panel shows rather simple models, maybe with two-dimensional ocean circulation, but the bottom panel shows fully three-dimensional ocean general circulation models. And you see that they have, you can see there would be a parabola lying in there, like on the left-hand side, in these what we call hysteresis curves. And so this schematic on the left is really supported by sophisticated model simulations. Now the big question is, let me just go back to that slide. The big question is, how close are we to this bifurcation point, to the tipping point? Where is the present climate? Is it really where it's shown there, or is it further to the left? Then the distance to the tipping point would be larger. And that is the big unknown, really. That's why nobody can tell you for sure how close is this tipping point. There is a very large uncertainty here. We know it exists, it is very robust, but we don't know where it is. I often compare this to a ship entering uncharted waters where there are rocks under the water that you might run onto, but you don't know where they are. That's the kind of situation we're in with the climate warming. And just more recently, in recent few years, the people from nonlinear dynamics, not just necessarily climate, other physicists are more and more interested in tipping points and are looking at how you could possibly get an early warning when you get close to one of these. And it has to do, you can visualize it by this ball lying here in this potential well, as a physicist would call it, in just a kind of a bowl or so. And now if you push it a little and wait until it rolls back to its equilibrium, the flatter this bowl gets, the closer you reach the tipping point, because the tipping point in this case would change the system going from top to bottom in the diagram. And so when you are in the middle one and you push the bowl towards that hump in the middle, it will take more time to roll back to its original equilibrium. And this is what's called a critical slowing down. So when a system recovers ever more slowly from a random perturbation, that is an indication that it's approaching a tipping point. And this is being used now to analyze a data time series for AMOC. A pioneering study here was done by my colleague Niklas Börs from the Potsdam Institute. And he looked at various time series of the AMOC. They're all reconstructions because we don't have these direct measurements, but I showed you how we reconstruct the AMOC early on in my talk. And what he is looking at is a parameter that has to do with this critical slowing down. And all these curves kind of that are fitted there, the trend lines, they're all pointing upward. And the tipping point would be where they reach zero at the top of those panels. And you can see that actually quite a few of these, if not most, reach the tipping point here in the 2000s, 2020 or so, except for the red one that takes a bit longer in the left panel. But this is actually quite frightening indication that maybe we are quite close to the AMOC tipping point already. I haven't found anything wrong with this study. One always has to be cautious if it's just one study, and we don't, we start to believe things when different groups with different methods come to similar conclusions. So wait and see. It's, of course, being heavily discussed in the scientific community now. I can show you one more study that just came out last year, and this uses, again, proxy data for the last 1,000 years from this network of proxy data, tree rings, corals, sediments, etc., that's shown on the map on the right-hand side there. And it has reconstructed Atlantic multi-decadal variability, which is closely linked to the AMOC strength. And you see on the left-hand panel, it's a noisy curve. But what you can do now is you analyze this critical slowing down in terms of the autocorrelation of these data. And if you take the autocorrelation of all this noise, you see it's going up more and more in the last 100 years. And that is an indication of that critical slowing down. And the authors write in their paper that the Atlantic multi-decadal variability, which is closely linked to the AMOC, may now be approaching a tipping point after which the Atlantic current system might undergo a critical transition. So that's another paper trying to look at these possible early warning signs, and it's not looking good. But it's not only the AMOC in the north. I showed you earlier on that also around Antarctica there's deep water formation, ventilation of the ocean, this overturning to a part of it is driven from Antarctica and the other part from the North Atlantic. And just a couple of weeks ago on the cover page of Nature and going through the media as well has been this new study by my Australian colleagues that found that first of all, there is indication that the Antarctic bottom water formation is also already slowing down. You can tell, for example, on the right-hand picture, you can tell that by warm water accumulating there between 3,000 and 4,000 meters depth in the ocean, where normally it should be continually replenished with cold water coming off the Antarctic shelf there. And when that is weakening, you expect the deep ocean to warm there. And they did very nice high-resolution model experiments where they showed what the future holds. And This dense water, which then runs down into the deep ocean off Antarctica, actually forms on the shallow shelf areas around the Antarctic continent. And in the left panel, that's where those orange-red blobs are. That's where shelf water is transformed into high enough densities to then run over the edge and down the slope into the deep ocean. And in their model simulation, which reproduces this very nicely, this process, by the 2040s in the right-hand panel, all the orange is gone. This has basically stopped. And the lead author of this, senior author, my colleague Matt England from University of New South Wales in Sydney, has said to this that the Antarctic bottom water formation looks headed towards collapse this century. Maybe even earlier than the AMOC in the North Atlantic, but with equally dire consequences. So conclusions to this part of my talk. Down there, is this a clock? Oh God, I'm running a bit late because I still want to talk a bit about the public debate, but that won't take that long. I'm concluding my kind of Atlantic circulation tipping point part here. The key points is I'm really convinced the AMOC is weakening. We know it has a tipping point. We have known that for more than half a century now. It is still very uncertain how close this tipping point is, like we're moving into these uncharted waters with rocks where we don't know where they are. And these recent studies suggest maybe really too close for comfort, which would be a strong motivation to really try and stick to 1.5 degrees. And there's also trouble brewing in Antarctica, according to this latest study that has created a big stir in the scientific community. So I hope I'm allowed to still add 10 minutes about the public climate debate. So you see the flat Earth here. Now, the key issue for me with the public climate debate is that for decades there has been overwhelming consensus in the scientific community that there is human-caused global warming and that it's a big problem. That has been shown in many studies, polling scientists, etc. But the public doesn't know this. The public doesn't know there is a consensus. And so there is a big mismatch between the discussion in the scientific community and the public. It's not just that the public doesn't know there is anthropogenic global warming, like 40% of Americans or so that don't believe it. It's luckily in Ireland obviously not like that, I have just learned, and also it's not like that across Europe, I think. But the public doesn't even know that there is a scientific consensus. And that, of course, has a lot to do with the media reporting, always climate skeptics arguments, and presenting it as a debate, as if there are two camps. This is false balance that the media often present. So that typically hasn't happened recently, but 10, 15 years ago, whenever I was taking a taxi somewhere and tell the taxi driver I'm a climate scientist, he would say, which camp are you in? Do you believe in global warming? So that's a problem. There is, of course, something behind this problem, namely an industry really going to big efforts to promote doubt. Naomi Oreskes has done a great job in this book, Merchants of Doubt. Michael Mann really describes the hockey stick and the climate wars very well. And I think this Guardian title by Graham Redfern sums it up. Doubt over climate science is a product with an industry behind it. It is manufactured, that doubt over climate science. Here is a statistic of just 5 leading oil companies and the money they spend annually on climate lobbying, which involves, of course, a lot of disinformation in the public realm, as well as lobbying politicians. And you see here, I mean, the companies spend $50 million per annum to spread disinformation. Overall, over a number of years, we're talking there about going into $1 billion or so, just spent on disinforming the public. Then, of course, there are a lot of gullible pensioners that like the message and spread it on Twitter, etc. Not because they're paid, but because it fits their worldview, etc. One example that we actually studied and were able to study because internal documents became available due to journalistic research. And we published a paper on this in Science earlier this year, is the Exxon papers. And Exxon actually had scientists doing their own climate projections. They built their own models or used models from the academic world, etc. And since the 1970s, they have been doing these projections. And now that they became available, we compared them to observations. All the gray and light dark gray lines are Exxon projections. They get darker the later they were made. So the earliest is the lightest gray, the dashed line going way up from the 1970s. There, they even overestimated global warming and expected a lot more global warming because the models were still incomplete. Later on, since the 1980s, they were pretty spot on with what really happened, namely the red curve. At no point did they expect that there was very little or no global warming, but in the public, they were always spending hundreds of, well, at least dozens of millions of dollars to tell people that lots of nonsense like only humans emit only 2% of the CO2, the rest is natural, etc. All these memes that circulate until this day in the social media, they were often generated by well-funded think tanks funded with oil and coal money. And actually, the UN General Secretary, just the week after our study appeared, was at the World Economic Forum in Davos, and he referred to our study and wrote that said in his speech, just like the tobacco industry, they rode roughshod over their own science. Big oil peddled the big lie, and like the tobacco industry, those responsible must be held to account. That is an interesting legal question that I won't go into now, whether you can hold these people to account for disinforming the public. Just a couple of examples of typical fake paleoclimate arguments. Just recently, again, a very high follower account was showing a curve that was supposedly global temperature. The argument always being, well, climate has always changed, there's nothing new. And you see at the very end of that panel there, where is it? The top one here, present global warming is practically invisible. Now, why is it invisible? Because it's a Greenland ice core that ends before modern global warming started. And it also has nothing to do with a global mean temperature. These big ups and downs that you see there at the end of the last ice age have to do with instabilities in the ocean circulation and have no effect on global temperature. And if you look at the Greenland ice core, at Greenland, it's now warmer than any time in the Holocene in Greenland as well. And for the global mean temperature, of course, I showed you this before. This is just where we are now. We are well outside the Holocene. And even on the top left graph, you see the temperature scale on the left says it's central Greenland, and it has temperature minus 40 degrees. It has nothing to do with global temperature. But at least on this graph, you can still immediately see the lie here in the title, Earth temperature. On others, they are simply presented as if they are global temperature curves. And as an expert, you immediately see, it's a Greenland ice core. And the modern warming is missing. That happens again and again, and you can debunk this again and again, it doesn't stop. This is also a very recent one, actually, from this January. And Steve Milloy is a very well-known climate denial perpetrator for decades already. He earns his money with this. And he says that the last 8 years, global cooling at a rate of 0.11 degree per decade, despite 450 plus billion tons of emissions, worth 14% of total man-made CO2 in the atmosphere. CO2 warming is a hoax. That is a typical example of cherry picking that happens again and again because there's noise in the global temperature series due to natural variability, and there are always periods where temperatures are stagnant. This is the how skeptics see global warming, like those blue curves. They always find portions where there is no warming. And now the red line is how scientists see global warming. This has been, this discussion, we had this in the 1990s, etc. Every time it happens, when you can find a little segment of the curve that has no slope or even slightly going down, the skeptics cry, global warming has stopped, or global warming is a hoax. Similar thing with sea level here. Björn Lomborg, he's another very famous perpetrator of disinformation for decades. He even got this into The Guardian. He wrote in this commentary in The Guardian, over the past 2 years, sea levels have not increased at all. Actually, they show a slight drop. Should we not be told that this is much better than expected? This always kind of insinuates the climate scientists are alarmists. They're telling you something that's wrong, and really the sea level is dropping. When he wrote this, actually that little drop was already over, because these data are always really current on the internet. Everyone can look at the satellite sea level record. And well, if I were earning $775,000 annual salary, as Lomborg does with this kind of stuff, I would be quite happy. I wrote an article about Lomborg, if you want to know more about him, at our blog, Real Climate. This is just a nice example of cherry picking, one of the standard methods of climate denial. This is what the real sea level curve looks like. It doesn't always just rise, it accelerates actually, because of course the warmer it gets, the faster the ice melts. And the little blip that Lomborg commented about is highlighted again here on this longer term curve. This is just classic. This is a kind of funny thing. This is, I think, couldn't happen in Europe, but in America, Virginia actually banned using the term sea level rise in official documents, because sea level rise is a left-wing term. You can only laugh about this, but in a way it's really serious. But we don't have this so much anymore, this kind of denial. In Europe, not. In US, yes, with Trump, of course. This is, I think, my final slide, almost. The debate really has shifted away from this, at least in Germany, it has pretty well completely shifted away from this denial of that there is warming, that it's human-caused. And we now have these discourses of delay, and also the debate has shifted to the solutions. There's a lot of fake news about wind power, about solar power, about electric cars, batteries, heat pumps. I won't go into all the disinformation here, but I could quote a lot of examples here. What are these discourses of delay? There's a nice cartoon overview there by a French person, Léonard Cheminot. The website is on the top here. Just a couple of examples. Whataboutism every day on Twitter. What about China? What does it help if we reduce our emissions? What about China? Point to others. Or this individualism where it's the individual who is blamed. It's not the fault of the power company to produce coal power. We are buying it, but that consumers often just simply have no options. That is often left aside. Then no sticks, just carrots. We have a party in the German government now that has this very strongly, that everything should be voluntary, and politicians like to hand out subsidies, but they don't actually like to ban fossil heating systems, for example. And then the social argument. In Germany, it's the social justice appeal. It's typically the nurse who needs her car to drive to her job, or the poor pensioners who wants to fly to Mallorca, and so the air tickets can't be expensive. These are people that typically uttered by people who never care about social justice, except when it comes in handy to stop climate measures. So I'm closing now with a quote from the synthesis report, which really sums it up. There is a rapidly closing window of opportunity to secure a livable and sustainable future for all. This is a very high confidence statement. And the choices and actions implemented in this decade will have impacts now and for thousands of years. This is also high confidence because of the long timeline of sea level rise, of the CO2 remaining in the atmosphere, and so on. And what we need to do is go the blue path, very rapid emissions reductions. We're still on this red path, which is progress. In the past, the emissions have always risen. We now have climate policies in place worldwide that will probably keep them level from now onwards. We're already seeing this plateau developing, but that's just simply not good enough. We have to go down very rapidly to avoid a disaster. With that, I thank you very much for your patience. I overran my time. I apologize for that. And if you want to read more, have a look at these books. Thank you so much. Thanks. So, this one?
Yeah. Thank you so much, Stefan, for a fascinating, if terrifying talk. And I can imagine people listening, and to a certain extent with regards to AMOC collapse and the tipping points, the response could be understandable. What is the point? So how do you combat what could be seen as a kind of inertia in response to what you're suggesting?
That's a difficult question, really. I think from my point of view as a scientist, I have a clear idea what my role is, namely inform the public as well as I can. But I think that is not enough to really shake people out of their inertia. That has been shown by basically decades of scientists warning about this, and the response being really lacking. And I think that just we need a lot more people getting involved in this, artists, writers, media, film people, for example. We see now worldwide, I think, and also in Germany, that the medical profession is quite strongly getting involved and telling the people what a public health threat global warming is. They're talking about planetary health. So I think it shouldn't be left to the climate scientists who just kind of tell the facts like I do, and that is of course important. We need those facts, but it's not enough. So we need many more people, including of course the young people, and what Greta Thunberg did by just sitting with a board in front of the parliament every week and triggering a global youth movement with millions of people, young people involved, just shows that the time was really ripe for what she was doing, that the young people feel strongly their future is threatened and are taking to the streets. And that's also important to overcome this inertia. Talk to others, join others in action, go to climate protest, and it makes you feel better yourself as well, because it overcomes that feeling of hopelessness when you feel you're alone with a problem that's far too big, you can't solve it.
Should we have hope if the tipping point has been reached with AMOC? I mean, we were speaking before and you were saying there's a possibility that already we have reached the tipping point. And you won't necessarily know. It's not like a fire will be lit. It will happen over time and scientists will reach that kind of consensus or not. But is there a reason to still have hope if that is what has been reached?
Well, first of all, we always have the hope that we haven't crossed the tipping point yet. And it's just that with every 1/10 of a degree of warming, the risk that we have crossed the tipping point gets bigger and bigger. And so, of course, there is still the hope that we haven't crossed it. And even once we have crossed one tipping point, we still have to fight to prevent crossing further tipping points. I showed you that there is quite a few tipping points in the climate system. And I think if you just more generally want to know, is there a reason for hope? I would say, in a way, I'm more pessimistic about the tipping points now, but I'm more hopeful that we can solve and stop the warming than I was 10 years or 20 years ago, because the technologies like renewable energy, electric vehicles, heat pumps, all these things are available now, and they have developed much better than even the optimists have hoped, both that the renewable energy generation is growing exponentially worldwide. The International Energy Agency has said that more than 80% of the power sector investments are now already going into renewable storage and grids, exactly what we need. Wind and sun alone have overtaken already nuclear power, and they're growing exponentially, and the prices are massively coming down, a fraction of what they used to be, and still coming down. So I think there is very good reason now to be more hopeful, because we have the means in our hand to get out of fossil fuels and stop the warming very quickly.
But you have hope that we will dip below 3 degrees, which, as you say, the plateau is looking like it's on that trajectory.
Because I see with the current climate policies, we are not on a trajectory of rapidly falling emissions, but I see that we have the technological means, and that governments around the world are increasingly aware of this. And you mentioned, I think, yourself, that there are social tipping points. I have seen the Berlin Wall fall, which for decades nobody thought possible. And, at a certain point when the people really demand change, really drastic or very effective climate policies from their governments, and the governments realize that they are voted out otherwise, I think we'll see a big change as well. Now the governments are afraid they are voted out when they tell people they can't buy a new oil heating system anymore, they have to go for a heat pump. Politicians are afraid they're voted out when they do this, but they should be afraid they're going to be voted out when they don't really make climate policy their top priority.
Can you give, and if anyone wants to ask a question, we are fairly time limited, so please just start waving at me and I'll get a microphone to you. Can you give an idea of what the implications are if the AMOC starts to shut down, if we've reached that tipping point? So if, the equivalent of a Hollywood producer coming to you and saying, right, we're going to do a film about it, stick to the facts. What is that future for people?
Well, the thing is that it will be a massive change to the energy in the system, the gradients of temperature. You have then one region that cools, surrounded by regions that warm. The problem is that it's difficult to exactly say what will this do to our weather, for example, because that depends on the jet stream and things that are not necessarily extremely reliably predicted when there is such a really change to the system, the whole dynamics of the flow in the atmosphere. So I would say there's going to be major changes to extreme events, stuff that we have never seen before, but I couldn't tell you exactly what it is. I mentioned the sea level rise that would be massively enhanced, a big threat to marine biology in the North Atlantic. If you get not the deep water formation, you get less oxygen being supplied to the deep ocean, which will have a major impact. And I also mentioned the less upwelling of nutrient-rich waters. So the whole fisheries, which are at the end of the food chain of marine biological production, of course, that would be a huge disturbance, which I can't really describe in detail because nobody knows what it will look like.
Can I ask just your own personal motivation for doing talks like this, and you do so many? I'm mindful that you were a PhD student back when James Hansen, the climatologist, told the US Congress in 1988 that global warming had begun. He said it's already happening now. What kind of impact did that have on you then? And why have you found yourself jumping outside of your science and pursuing this sort of parallel career in public communication?
Well, I was certainly already in the early 80s aware of the global warming problem because, one simple thing I remember is I did my PhD in New Zealand in 1987. I went there, and in those 3 years that I did my PhD, I never flew home. I missed my sister's wedding because I was worried about the CO2 emissions in the 80s. So not many people were that worried back then, actually, but I certainly was. And when Jim Hansen in 1988 said global warming is here, we see it now in the data. It's not just a forecast anymore. That was in the science community, it was a bit controversial whether he was leaning out the window maybe a little bit early, whether it could still be natural variability. That's what some more conservative professors said back then, but of course nobody thinks that anymore now because it's blatantly obvious. I did get involved in the public communication. I mean, in a general sense, quite early on, because I benefited that much as a schoolboy myself from reading science books, popular science books, that I always thought it has high value to explain science to ordinary people, non-scientists. But in this kind of skeptics issue, I got really involved after the Elbe flooding in Germany, which flooded the city of Dresden, one of Germany's major historic cities. 2002. And, I was in Dresden at the time for a TV talk show. I was invited there and I saw the flooded city all in dark, no electricity, etc. It was quite an impact on me personally. And then a week after, I was in a panel discussion where I was confronted with somebody putting up a slide of a so-called proof that global warming was caused by an increase in solar activity. And I knew that paper, I knew that had been retracted. It was bad science. There was a very simple fault in it. And that kind of stuff appeared then also in the media. And I thought, look, we can't as scientists just laugh about it in the coffee break or so, how stupid the media are. If we know better, we need to speak up.
And do you think, finally, before we go to the audience, do you think that climate scientists specifically, but in a broader sense, scientists in general, should have done more in the last couple of decades in communicating?
Yeah, I think so. I would have often wished that more scientists get involved, because they left it to a few people like Mike Mann or Jim Hansen, or more recently Catherine Hayhoe or so. And if it's just a few people speaking out publicly, then there's always what Mike Mann once called the Serengeti strategy, like the lions trying to isolate one zebra or so and run it down. Then the individual scientists get attacked if it's just a few. They get painted as outliers or unreliable or so, activists. And so I often wished that a much greater part of the colleagues would speak up. But they tell me, I have proposals to write, and you're doing it so well. I'm glad you're doing
Keep going.
this. So I don't have to get involved in this ugly public debate where people will just sling mud at you. So a lot of colleagues were hiding behind what the few people out in the media were doing.
A question at the back.
Hi there. Can I ask Professor Rahmstorf if he agrees with the UN Ambassador for the Oceans, Peter Thompson, when he spoke to the IIEA here in Dublin, post-COP26? I asked him if he believed an IPCC special report was required on AMOC slowdown or tipping points in general. He said AMOC loss could have massive consequences, and he agreed it merited further study. So do you believe the IPCC should move on this, or do you believe their synthesis report that we've just read is enough at this present moment?
The answer is yes, I do believe that a special report on this by the IPCC is a good idea.
Yes, in the front here.
Two-parter.
Mike is coming.
Just 1 second. Thanks.
The first part is where AMOC has collapsed in the past, how long has that process evolved over? Is it a decades-long process?
I would say, mostly based on the model simulations, that it would be a process that takes several decades.
Are there models, are there projections to 2100 that overlay the cooling effect of either AMOC slowing down by another 15% or stopping altogether, with projections for what is going to happen in this corner of the Northern Hemisphere if we hit 3 degrees. Has anybody put those two projections side by side and said, this is what the North Atlantic is going to look like?
Well, you know, I showed you some simulation results where there was several degrees of warming, like, I don't know, probably about 3 degrees actually, this one IPCC figure, or which showed this cooling due to AMOC slowdown in a world with about 3-degree global warming. Is that what you're asking for?
Yeah, and what impact does that then have on... Let me shortcut this, because I know you said you're not going to make predictions about weather systems, but given what you know about what is likely in that scenario, would you buy a holiday home on Ireland's west coast?
Well, it depends how close to sea level.
A quick question online here before we go back to the audience. Does the plastic pollution collecting in gyres affect the circulation?
Not that I know of.
Yeah. Question here.
Thanks, Stefan. You presented the climate model projections, which very consistently show an AMOC slowdown. And you showed a very kind of convincing compilation of the observational evidence for a slowdown in the past. But when you look at those climate models in the past period, through the historical period in the 20th century, they don't reproduce what you presented in the observations. So I was wondering what your opinion was on the implications of confidence in future AMOC projections when those same models can't reproduce the past.
You are referring to them showing not the same amount of weakening in the historic runs, right? Yeah, I showed you this paper by Latif, etc., with a correlation where this didn't actually lead to cooling, whereas the observations show a clear cooling. So that would indicate that the weakening is faster than predicted by the models. And there is, in fact, a number of reasons why the models may be underestimating this problem. Lack of meltwater from the Greenland ice sheet, because most of these climate models simply don't have melting of the Greenland ice sheet. They're not coupled in this ice sheet in many climate models. Also, this paper that I showed by Liu et colleagues, where they corrected for the salinity and then the AMOC became more sensitive, suggests that uncorrected models tend to be not sensitive enough. There's further evidence for that. Actually, there is scientific literature suggesting the models are too stable. The AMOC in the models is too stable. And also those early warning indicators that I showed there that suggest that the tipping point is maybe relatively close would disagree with the standard models which don't cross a tipping point this century. So yeah, there is a discrepancy there, and unfortunately it points to probably most models underestimating the risk.
We had a question from the Irish School Sustainability Network that work obviously with a lot of young people, and they asked, for those of us working on climate change and biodiversity loss, often others perceive this as an area of personal interest to us rather than a moral purpose. How do you think we can connect people to what is happening intellectually and emotionally? I mean, I thought it was interesting earlier you mentioned the role of artists and creatives in trying to connect. Perhaps also what you meant was also outside of the pure facts of what is in front of us.
Yeah, I think to connect emotionally, that's not the expertise of a physicist like me, but I think that, for example, screenwriters should, they don't have to make movies specifically about global warming. Maybe not so many people want to watch it, but this just as running as a background thing, because it affects all of us in, a crime story or so. Actually, such a series exists on Netflix now called Close to Home, a German one, which is set in the coal mining area in East Germany, open cast mining is a crime case, but with a background of a heat and drought summer and a climate activist camp there, then occupying the coal mine, etc. So just to pick up this strand of public discussion about the climate issue as a matter of everyday films, etc. I think just to get us to talk about it more, because there is a big reluctance. It's a kind of a party pooper thing to start talking about climate change. I was actually once in a meeting at one of the embassies in Berlin where there was a visiting scientist and, a visiting artist, writer, and several other cultural people there at a dinner table, and everybody was saying what they were doing, and everyone was interested. And when this woman was saying, the writer was saying, yeah, I've just written a book about climate change, somebody else immediately asked, oh, and what else do you do? Just quickly shift the subject when someone brings up climate change. Maybe you have had this in the family or at parties. We need to talk about this in order to solve this crisis.
It is uncomfortable, perhaps.
Yeah, it is uncomfortable, partly because it's unpleasant, but also because, unlike whatever immigrants or so, it's not a matter of opinion. You have to know a lot of science to be really talking about it. Otherwise, I think everybody probably who is not a climate scientist feels somewhat insecure whether they really grasp the facts and can withstand a discussion if someone challenges them on science.
I just want to finally ask you a question about this idea of societal tipping points. I know you did an interview when you were in Davos in 2020 where you said, I feel we're now near a societal tipping point where finally the majority of people are starting to grasp we are in a crisis situation and we need to act fast to avoid disaster. 2.5 years later, would you still say that's the case?
Well, I think we still are near the tipping point. Of course, the corona pandemic has been a big setback because people have simply shifted their attention to another big problem that affected their lives. And that also, in a way, really subdued the Fridays for Future movement because, just no big protests could be held, etc. But I still think, from my perspective, that we are close to that tipping point for several reasons. One of them simply being that, as I said, renewables are now the cheapest option. That is a tipping point in itself for where the investments are going, but also in the public awareness with all the extreme weather events. I think people are starting to wake up.
Stefan, thank you very much for your insights and for your participation this evening. We're very grateful. And thank you all so much here in the Mansion House and also everyone watching online. You will receive an email with a survey, and I know the EPA is very hopeful that you will give your feedback and your input for future events as well. I know also that the EPA would like to announce this evening that registration is now open for their annual EPA Climate Conference, which will be held in Dublin Castle at the end of May the 25th. Registration details can be found on the EPA website and will also be emailed to all of you who attended, and it's going to feature Professor Jim Ski as well. So just finally to thank Stefan hugely for his contributions this evening, for visiting Ireland for the first time since 1981, and we hope you won't leave it that long to come again. And thank you very much indeed, everyone here, for coming.
Thank you. Thanks a lot.